So last time we learned about how one can check the planarity of given graph, and then for given planar graph, how one can actually produce planar embedding. So what we will do today is we will, learn about how one can test given graph, whether the given graph contains certain minor or not. This is more general than checking planarity because by Grotowski's theorem, we know that a graph is planar if and only if it doesn't contain K5 or K33 as a minor. So in order to check the planarity, you can just check whether the graph contains K5 minor or K33 minor. So let's call that a family of graph or collection of graph as a minor closed family. If, the family is closed under taking minors. So, we all know what minors are. So if we have a collection of graph which is closed under deletions of edges or deletions of vertices and contraction of edges, then we say that they are minor closed family. So let's say, I didn't write the deletion of vertices here, but we can also delete the vertices as well. And many interesting family of graphs are minor closed. So for example, planar graphs. If you have a planar graph and you take the minor, then that's again planar. Or we can consider K-colorable graphs. Those are minor closed. So originally the graph is K-colorable, then you take the minor, then it is, also K-colorable. So, So in order to check whether a given graph belongs to this collection, so for this collection of minor closed family is given, and we want to check whether a given graph belongs to here or not. That's one of the important questions. But for that, we have this theorem by Robertson and Seymour, which said that when we are given a minor closed family, F, then we can always find the finite collection H of graphs such that the graph is in this minor closed family if and only if this doesn't have any H minor for all H in this given list, finite list of H. So for example, for planar graph, this H is nothing but K5 and K33. Because Grotowski's theorem says that G is planar if and only if it has no K5 minor and no K33 minor. And what Robertson-Seymour theorem here says is that the Grotowski theorem was not a coincidence. Not only the planar graph, but any minor closed family you take, you can always, find the finite list of graph. So that as long as the graph doesn't contain any of, minor in that list, then it belongs to the, minor closed family. So before we wanted to check whether a given graph is planar. Now what we want to do is whether a given, graph is actually belong to minor closed family, F that's given. Then based on this Robertson-Seymour theorem, what we have to do is we just have to check whether this G has an H minor for some H in this finite list. So now the problem becomes that instead of checking, if we want to check whether this graph G belongs to this, graph family F, what we need to do is for given H, can we check whether this G has an H minor or not in an efficient way. And indeed, one can actually test test this in polynomial type. So when we have a G and we want to check whether this G has H minor. And let's fix H. Then what can show is, let's say this G has n vertices. Then we can check this in a time, a polynomial time in n. In time that is a polynomial in n. So this is quite efficient algorithm in a sense that it's only polynomial in n. However, in this polynomial, actually looks like there is some constant depending on h times some polynomial in n. So there is this implicit constant which comes from h. And this is actually very big in terms of h. So for fixed h, this is only constant. This doesn't grow. But it's not practical because this is usually very large. So anyway, so we will kind of describe, how one can do this. One can check whether given graph G contains H minor. So for that, we consider this K-linkage problem. So assume we have in graph G, assume we are given some pair of graphs, pair of vertices. So x1 and x2. No, let's say y1 and x2, y2, and let's say x3 is, again same as x1, and y3, and y4 is same as, same as y3. No, let's say y4 is same as x2 and x4 is same as y3. So some pairs are given, ordered pairs of the vertices in a graph G is given. And in K-linkage problem, it's asking whether there exist K internally disjoint paths such that the ith path has endpoints xi and yi. So for example, what we want to find is one path connecting x1 to y1 and x2 to y2 and x3 to y3 so that it's internally disjoint. So it doesn't intersect with any vertices in the previous path, and x4 to y4. So we want to find these 4 internally disjoint paths. So internally disjoint means that this path and this path only shares on this one endpoint, but everything else is disjoint. So it's known that for fixed K, the K-linkage problem can be solved in let's write it this way. So in G, we want to find the K linkage. Then let's say G has n vertices. Then it can be solved in the polynomial times in n. So n cube. But again, this time is some constant which depending on K times n cube. And this constant depending on K, which doesn't depend on n, is large. But still, we know that such algorithm exists. We will, actually skip the discussion about this algorithm, and it's, because it's complicated. But this is something that's known. One remark is that before we consider the k-linkedness. There we take two k vertices which are all distinct. We consider x1 to xk, y1 to yk, and then we want to make sure that all 2k vertices are distinct. But here we don't impose that condition. So this is more general problem. And from this definition, and this result, that you can find you can solve this k-linkage problem in polynomial time. So one can actually, if you want to just test H subdivision, testing H subdivision can be done in polynomial time. What do you do is, once you have say your H, say this K4 is your H, then what you do is you consider these 6 edges. And in G, you pick 4 vertices, x1, no, let's not write x1. You pick 4 vertices. And then you take this as x1 and this as y1. And you take this as x2 and this as y2. And this has x3, and this is y3, and this has x4, and this is y4, and this is x5, and this is y5, and this is x6, this is y6. So you pick 4 vertices. So that, there are n to the 4 way of doing this. And then once you fix that, now you want to give this name, and then check whether there are, internally disjoint paths connecting x1, y1, x2, y2, x3, y3, x4, y4, and x5, y5, x6, y6. So this is actually checking subdivision whose branch vertices are these 4, which can be done with n to the 3 times. So each time, checking can be done n to the 3 time, and then you have to do it n to the 4 many. So this can be done in n to the 7th time, which is again a polynomial. So for fixed h, you only have to do n to the h plus 3 many, times some constant. So this is the polynomial in n. So you can actually test whether the given graph contains H subdivision or not in polynomial time. But for the minor case, so here you have to pick these 4 branch vertex, and then you check the edges between. But for minor, this branch set, so instead of in the subdivision, you have this 1 branch vertex for each part. But here in the minor, what you do is you contract this blue part, and each blue part becomes 1 vertex, and you get, say, here K4 subdivision, K4 minor. So before, we have to just choose 4 branch vertices. So there are n to the 4 way of doing that. But for minor, we don't know how large this branch set is. This could be a large set. And we have to choose 4 such large set. And then we have to check whether, you can find the edges between here and here. So, the previous trick doesn't work. Here, we only have n to the 4 many choices. But here, once you take this 1 branch set, for all we know, there could be exponentially many choices of connected subgraph. So that's the problem of, directly applying the idea of finding this subdivision. So this wouldn't, yield a polynomial time algorithm. But what we do instead is, using this idea. So assume you have this K4 minor. Then, for example, these vertices are pretty much useless. And these vertices are also useless. Even if we delete them, this is still minor. And even if we delete some edges, it's still, K4 minor. So if you, leave some, let's use other color, purple, it is more visible. If you use some absolutely necessary one here, then it's enough to take just this part. So as long as this branch set is connected, you don't really need anything more. So you just take a spanning subgraph, and then you can forget the rest of the blue part. You only consider this purple part. Moreover, for now, for our convenience, let's use which color? This color. For our convenience, let's subdivide each red edge twice. We will see why the reason why we do this is once we subdivide this twice, and then you consider this as well here, this as well in this purple part. Then here we have this purple part is a tree with exactly 3 leaves. And okay, sorry. So this is actually not necessary because this 2 is already connected. So here again we have this purple part is a tree with exactly 3 leaves. This is again tree with exactly 3 leaves. And if you add this, then this is tree with exactly 3 leaves. So this degree is 3, then here we get a tree with exactly 3 leaves. But this tree could be huge. There could be many vertices in here, right? But still, this is, even if there are like many degree 2 vertices here, then those can be, so one observation is all this purple tree is always a subdivision of a tree with 3 leaves. So this 3 is actually a degree of some vertex in H. So this gives us that we don't have to consider all branch set, but we only have to consider the branch set, which is a subdivision of a tree with exactly 3 leaves. But again, we are more well equipped with testing this subdivision. So that gives us the motivation, idea of designing this algorithm for testing H minors. So what we do, we first, consider each vertex H of V, which has a degree D. Then we choose a tree with exactly D leaves with no vertex of degree 2. So every time you have one more vertex of degree bigger than 2, you get more leaf. So if you fix the number of leaf, and then you assume that there are no vertex of degree 2, then the number of vertices in a tree is bounded. So there are only finitely many ways to, finitely many such tree. Here, finite means that this depends on D. In other words, this depends on H. Now we said that we fixed H. So any constant, any number that depends on H is just a finite constant that we don't really care much, because our goal is to find an algorithm which solves the problem in polynomial times in n. And n depends on the size of the given host graph G that we want to check. So anything comes from H is just finite. I mean, just a constant. So there are finitely many such trees. So we calculate all such trees and then we write a list. So there are finitely many of them, and we consider all choices of such tree for each p in H. So meaning that you have H, say this is H, then you have 4 vertices. And for each vertex, we can choose one such tree with 3 leaves. And for here, another choice, another choice, another choice. So if there are like m choices of such tree with 3 leaves, then here m choice, m choice, m choice, m choice, we have m to the 4 choice. So again, these choices are finite, because this previous number, you take the power of number of vertices of H, so which is again a finite choice. And for each such choice in the choices, and we also again now consider the number of ways to add edges between two. Say you have this one tree with 3 leaves and this one tree of 3 leaves. Then the number of ways to say add edge between this and this is either this or this or this, or this or this or this, or this or this or this. There are 9 ways, right? So what we do is for each UV in H, for each of these, so now this is U, this is B, and this tree is representing U, this is chosen for U, this is chosen for B. Then we want to add an edge. So we want to add either this or this. There are 9 choices, you choose one. So we match a leaf from the tree for B with a leaf from the tree for U and V. Sorry, I wrote here. In such a way that there are 3 more here, 3 more here. And we add in a way that that every leaf is matched exactly once. Then we get a graph. And because again there are finitely many choices of these, and there are finitely many ways of adding matchings, matches the leaf. So the result is there are finitely many ways of, finitely many graphs. And then finally, so this graph that we obtain is exactly, the graph here. The graph here up to subdivision. So here, these are vertices of degree 2, but we contract it, and this is again this 3, and this is 3, so K1, 3, because this is branch vertex, this is 1 edge, this is 1 edge, this is 1 edge. If you contract all the vertices with degree 2, then again this, and this is 1 edge, and here, this is 1 edge, here, and then through this red one, these are, added. So these are the edges that, I mean, the matchings that we add between the leaves. But now, I mean, these orange ones are actually not there. That's artificial one that we added. So we want to get rid of that. So now we contract each pendant edges of the original tree, meaning that in this tree, these are pendant. So we just contract. Contract meaning that those yellow subdivisions are gone. So we contract each pendant edges of the original tree. Now these three edges become one edge. They each one edge represent each edge of H, and let's say the resulting graph is H prime. Then this H prime contracts to H by contracting each tree. And moreover, this shows that whenever we have a H minor in G, then G always contains a subdivision of such H prime. One of H prime. There are many H prime here. So this shows that if we want to check check whether a given graph G contains a H minor, you can instead check whether it contains a subdivision of H prime. So here in this specific case of when H is K4, the H prime you get is always same as, because here we have only one tree with 3 leaves having no degree 2 vertex, and 1 and 1 and 1, and then once you match them, no matter how you match them, and you contract this leaf, contract, then what you always get is K4. So this actually is correct. This is not surprising because we know that having K4 minor is same as having K4 subdivision. For any H with the maximum degree m mod 3, having H minor is same as H subdivision. So in this specific case, we get K4, but for more general H, you get not only one, but many lists of H prime, that we get here. So now, now what this says is that testing H minor is same as the, testing H, say, I subdivision. So let's say H prime subdivision for H prime in some finite list. This list is what we obtained above. And the number of, this graph here is a constant. This L is at most some constant depending on H. And each time, checking each H prime subdivision can be done within the polynomial times in N. So this shows that for fixed H, the testing H minor can be done in polynomial times in N, when the N is the number of vertices in the graph G, which we want to check whether it contains H minor or not. But if H is not fixed, so this is fixing H, and then we let G as a input. Then our algorithm gives us that some constant depending on H times N to the some other constant depending on H. This is the time that requires to check the check H minor. But if H is also an input, then the problem is much more difficult. It is NP complete. And we know that if K is a part of the input, so K is not fixed, then K linkage problem is NP complete. And also testing for, H as a minor is, again NP complete if H is a part of input. So for example, if H has a, n vertex cycle and G has n vertex, then G contains H as a minor is same as G contains a Hamiltonian cycle. And we already know that checking whether a graph contains a Hamiltonian cycle is NP complete. So this minor problem is as hard as Hamiltonian cycle problem. So, so it is NP complete in general. So this, so we have learned about the algorithm checking the, minor in a given graph G. And in the next video, we will move on to the next topic of considering a complete minor in a given graph.